Okay, so now we're gonna discuss regarding the last module for the exam. Hopefully, we have one more week to discuss about membrane separation, but it is not included in the exam. Okay, so this is actually the topics for the final exam or WAS, yeah, or the module 3 exam about extraction. Okay, so uh, once I still gonna start with this presentation. Okay, yeah. Okay, so the extraction, the very typical or very simple example of extraction is the solid liquid or leaching. You can find it every day, and then you may do it every day. Okay, because this is while making tea. Yeah, when you want to make tea, so from the tea bag, for example, you put it in hot water. You prepare a hot water, and then you put the tea bag, yeah, into the hot water, and then wait a little bit. Yeah, sometimes you stir it, sometimes you add the sugar as well, and then if the water is very hot, almost 90 degree, it's just gonna be, and then uh, uh, you also agitate it, yeah. Did You will have a very dark tea, the dark color of tea in just a few seconds. Okay, that is an example of leaching. Okay, leaching is a solid liquid where we have two type of phase, and then the solute the solute is transferred from one phase to another. Okay, in this case, the solute is transferred from the solid phase into the liquid phase. Okay, now in the extraction, what we call it is actually it reverts to liquid extraction, where the if we have some a solute in one liquid is transferred into another liquid. Okay, so uh, uh, another part, for example, an example is liquid extraction. So the one that you have every day, maybe, yeah, is the making tea. It is a type of solid liquid extraction, or it's called leaching. Okay, but now what we're gonna talk here is about liquid extraction. Yeah, later on in the calculation, it would be quite similar. Okay, so in the liquid extraction, there are two liquid. The first one is the liquid where we have the solute here. Yeah, we have we call it the first one. We call it original solvent, or A. Let's say the compound A, and then we have the solute. We can call it C, and then we also have the extracting solvent, uh, for example B. Okay, um, I think maybe you only see the videos, but I did some experiments in when I was in a second year in organic chemistry, where we at the time at one group we have to extract the in, or call it the thein is a active substance from tea. Yeah, so at that time we uh, uh, we do at that time. So just make it blue, yeah. So at the time we perform an experiments. uh, Maybe you want to have a look on the YouTube videos, or if you still have your laboratory videos about how to extract thein. It looks like caffeine, yeah, from coffee, but it is thein from tea. uh, the tea bag at that time, if the first one we dissolve it in hot waters, yeah, uh, dissolve in hot water, and after that we will have the tea in the hot water, and then it is extracted by a solvent, yeah, a solvent, and then the solvent or hexane or something, and then here there is a solvent, the liquid extraction. Okay, um, based on um, the the properties or the substance, the tea or the solute in the water. So let's write this is water. It is more attached to the solvent in the extraction solvent, maybe based on the compound of the substance. Maybe some of them is non-polar, or maybe yeah, it's non-polar, so it attached to the organic solvent. Okay, so that is the principles of why the extracting solvent can uh, take or can absorb or yeah, can um, dilute the solute. Okay, so basically what happened when we contact them, when we contact the tea and the solvents, basically I think in the lab there is a solvent, yeah, solvent extraction like this, and then there's a valve in it. Okay, so basically here we add the tea, the water. So this is water and tea, and this is the solvent. Okay, so we put it in a, what, I don't know what the name is, the chocolate we call it, yeah, and then we mix it. Yeah, we mix it for a few times, mix it for quite a long time until there is a contact between the water and the solvent. So the liquid and the liquid one and the liquid two, or the original solvent and the extracting solvent, must be contact with each other, and then when it have a contact with each other, then the solute will transfer to the other part. Okay, so here there is a mixture here, and then the solute will diffuse to the extracting solvent, for example in this case. And after that, once we know, for example, the time when looks like the solute has transferred to the extracting solvent, after that we stop the process of the extraction, and then we wait. Okay, usually because of there are difference between the tea, sorry, between the water and the solvent, for example the organic solvent, there would be some difference. Looks like oil and water. Okay, they have different density, they have different polarity, so in the end they will separate. Okay, so in the end we will have a separation, and then at the end of the process, we will have the liquid that is rich in the extracting solvent that is rich in solute, and the original solvent would be depleted of the solute, for example the tea. Okay, right. So that is the principles of extraction, and so in the operational scale, in plant scale, the extraction process is carried out. So it should carry out the mixing process. The mixing process where the liquid 1 and the liquid 2 should be mixed together, and they should be in contact together, and then the solute can transfer from the liquid 1 to liquid 2. Okay, and after that, after the mixing is maybe the time is quite finished, what you do is you stop the process, and there is a settling. In the settling, the liquid 1 and the liquid 2 will be separated, usually based on different density or different polarity. Okay, and then usually it may be used in batch system, but we also see also some the continuous, of course we also have the continuous system for extraction. Just an example, in for example another example of extraction process, rare earth metal. So rare earth metal is the, if you look at the periodic system periodic, it is lies at the bottom there, the lanthanides, yeah, the lanthanides, and it is the all the rare earth metal are very close, the very close properties. So how to separate them, we use extraction process. So the rare earth metal are diluted in the some solution, for example aquatic solution, and then it is contacted with a type of organic solvent, or it is proprietary, and also yeah, there is a trademark name, yeah, for the solvent. And I did some research on a rare earth metal to separate, for example, the neodymium. Neodymium is the, where is, okay, neodymium, for example, from other compound uh, of the rare earth metal. I couldn't remember the other compounds. This is for strong magnet. They need up to 90 mixer and settler. Yeah, so those type, the mixer and settler, it can be written as one stage. Yeah, so if you remember about distillation, you need some stages to separate the vapor, compound A and compound B, in one in vapor, one in liquid, for example. In the top and the bottom, you need several stages. And in the absorption process, you also can calculate the height between HTU and NTU. And also the extraction process, later on we will also calculate stages. And then for neodymium and other compounds in rare earth metals, because they have a very similar properties, they may need 90 something stages. Yeah, so it is a very and how to calculate that, that's the one that we're gonna calculate. Okay, so it is it may be in a batch system, for example mixer and settler, sometimes in the mixing and settling. Okay, so why I'm telling you this, the application of the unit operation, because we as chemical engineers, we don't only calculate. The calculation is just a tool, but the much better if we can know the application of this this unit operation. Okay, so again, similar to distillation, yeah, if you in the distillation and also absorption and also extraction, you familiar with equilibrium, and also another one, operating line. Yeah, in extraction it's also applied. Okay, so you need the equilibrium data and also the operating line data. Okay, so but now the equilibrium is a little bit complex, because you have if you look at here, so you have one, the original solvent, B is the extraction solvent, and C is the solute. So you have three compounds now, compared to the two compound at distillation. Now you have three compounds for extraction. Okay, so the equilibrium is of course influenced by the pressure and the temperature, and also the equilibrium data is always empiric. So even we in my few months ago, when I studied this rare earth metal, at that time there is no equilibrium data for this separation. Yeah, so I read a paper from Batan, yeah, the Pusat Tenaga Nuklir, what they do is they make this one. So they calculate, they perform some experiments to find the equilibrium data. So they want to find so once we know the equilibrium data, then we can think how many stages, for example. Okay, and then um, unlike the distillation, where they have a very good thermodynamic model for vapor and liquid, for extraction there are not much data for the equilibrium data, so forecasting would be difficult and also unsatisfactory. So usually in a uh, typical process, typical application for extraction, usually the plant itself, the R&D in the plant, usually make the equilibrium data first to get the good empirical equilibrium data, and after that they do the calculation to find the operating line and then find the stages. Okay, so yeah, so this one is just the extractant, yeah. So here we have, just to summarize, we have three compounds. We have the original compound, we call it A, and then we have the original solvent, we call it B. The solvent, extractor, and then the solute, yeah, the pink one is the C. So there are three compounds. Okay, and then this is just want to show you again about the application, the schematic of it. So this one, for example, is the compartment mixing vessel with variable speed turbine agitator. So we have the feed, which is the mixture between the initial of liquid and also the extracting liquid, and then they should be contact them together with this agitator, and then the agitator also with this the power, yeah, it is should be with the variable drive, with the variable speed drive unit. And after that, after maybe sometimes we use the buffle or the compartment spacer, and after that it gonna be contact them together, and then they will have the emulsion. The emulsion is actually looks like if you have uh, oil and water together, and then you mix it so much, then at the end it looks like white or emulsion like that. And after few seconds, then the oil then became separated again from the water. Okay, and this case, this is the emulsion, because when we put the feed in the liquid, the initial solvent and also the extracting solvent, they will just contact them together, and then we got the emulsion out. And once the emulsion is out from the mixing, we go to the acetylene, or for example, an example here is the horizontal gravity setting vessel. Usually the one particular solvent is lighter compared to the others, and they will also doesn't have a miscibility, nggak terlarut ya, because they have different polar properties something. So here we have the buffle, and then the emulsion gradually will settling based on the density. So the heavier liquid will be in this way, and then the lighter one would be transferred into this case. And then at the maybe at the interface, we also have the tab here for the scum. Okay, so here the side part of horizontal gravity settling vessel. Okay, so yeah, up to here, any question? Okay, still listening. All right. Let me know if I'm too fast, or if you want to ask any question, just open your microphone and then ask question. Yeah. Okay, so how many components that we're talking about in the uh, extraction? How many components?
Mhm.
Three. Yeah, there are three components. The first one is the original solvent. The B is the extracting solvent, and C is the solute. Yeah, so we will have three components. Okay, so the extract phase will have three components. The one is the first is the solute. I will start writing the solute is a C. Why? Because this is gonna be the norm or the convention for the next graph. Yeah, so let's just put it C. Uh, the second one is the solvent or the extractor. We call it A. Okay, and then oh, sorry, this is the extract phase. Yeah, the solvent, the extractor, it should be B there. I think I should yeah. But before we talk about this, I think it's good idea if I want to explain what is extract and also raffinate. So based on this mixer and settler, maybe I just make it slow like this. Okay, so just to show you here that we have the mixing, which is um, let's say the emulsion. Yeah, so we have the feed. We also add with the solvent. Yeah, when it mixing together, after the mixing they will reach equilibrium. Okay, so the time when we stop the mixing is actually when it reaches the equilibrium, where the solvent is in equilibrium. The solvent is more attached to uh, the solute is more attached to the solvent. And after the mixing here, it will separate into two phase, right? The usually one is called this liquid. One is called extract. I don't know which one is the extract. Yeah, because I don't know which one is the lighter or the heavier, and the remaining or the original solute, the original solution is called the original solvent. I mean, is called the raffinate. Okay, so I don't know if the extract is lighter, then this is the extract and this is the raffinate, the heavy one. If the extract is heavier, so this is the extract and the other one is the raffinate. So it's basically once you perform the extraction, when you separate it, one become extract, which is rich in the solvent, which is rich in the solute, and one is the raffinate. Okay, so now we can go back to here. So the product, okay, so the product now, we have extract phase, and then we also have raffinate phase. The extract is the one that is higher in the solute. Okay, for example, we uh, make the tea, yeah, with the so the water is act as the extractor. Okay, and the thein or the tea will dissolve from the tea bag, from the solid one into the liquid. Now the tea, the water contained tea now is called the extract phase. Okay, and then the remaining of the tea bag is called raffinate. That is a case for solid extraction. Just an example. But for in here, when I contact the tea solution and my original solvent, on my solvent in the lab, in the chemistry lab, and then I mix them together, and then when I separate, the phase that is rich with the tea now become the extract phase. Okay, and the one that depleted is called the raffinate. Okay, any questions? No? Okay. Just let me know if you have any question, yeah? Okay, so the extract phase will have three components. The first component is the solute, or I would like to see, and then the extractor, or the solvent that extract the solute, maybe B, but again, maybe there are still a little of the original solvent of the A, okay? It do happens. Maybe some of them just put into it just inside the extract phase. And the second one, which is the depleted depleted solute, is the raffinate. So the raffinate contain the original solvent. Here, for example, in my water and tea, which is contacted with the organic solvent, at the end of the contact, my water would have a small solute there. Okay, so this is the original solvent, or the A, and the solvent itself, the extraction, or just very small one maybe, and then also the solute. Okay, so then the equilibrium will contain two phases, the extract phase and also the raffinate phase, and each phase will contain three components. Okay, so it's a little bit not difficult, you need more understanding about this one. Okay, so to sum up, that there are two phase from the product. It's called the raffinate phase and also the extract phase, and in each phase we'll have three components. Now, how to declare these three components into equilibrium phases? This one, we will learn the unit of equilibrium composition. As you can see in here, we will use the triangle diagram. Yeah, we'll use triangle diagram because it will have three compounds. Okay, but before that, let's have a look about what is this? The industrial liquid extraction process. Yeah. For example, it is a really it is very established. It looks like a distillation, especially for the hydrocarbons. For example, we have solute in water. When we want to recover the acetic acid, we can contact them with ethyl acetate, and then the acetic acid will transfer into the ethyl acetate. Okay, another one, if you have ammonia in a butane, so we contact them in the water. Another one, if you have aromatics in paraffin, it can be contacted with the solvent like the ethylene glycol and sulfura and so on. Yeah, even for if we still have glycerol from water, and then we want to remove the glycerol from the water, for example, we can contact them with alcohol, or the high alcohol, and then the glycerol will transfer into the high alcohol phase. Okay, and now after the glycerol transfers into the alcohol phase, what is next? And the next thing may be another stripping, another I don't know, another extraction, or so on. Yeah, they should be the next one. Okay, so even here, if we have vitamin A or vitamin E in the oil, and then you want to extract them, and then yeah, you use propane as that one. Okay, sometimes extraction is interchangeable with the distillation, because the one that if we want to separate the compound in the solute and also in the solvent, we can do that by distillation as well. Okay, but in general, extraction is preferred to the distillation for the following applications. The first one is where the dissolved or the complex inorganic substance in the organic or aqueous solutions. And also if we heat it up, or if we remove the component, it will have a color, yeah, sometimes, yeah. And then if we have a high boiling component, sometimes it is, yeah, the extraction become competitive with distillation. And then also if the mixture form azeotropes, or if the compound is sensitive to heat, yeah, because in distillation we use heat as the driving force to separate the compounds. Then if we heat it up, let's say if we want to separate essential oil, for example, and then there's a type of essential oil that is gonna be broken, rusak, yeah, if we increase the temperature too high. So what we do is actually we can use the extraction compared to the distillation. Yeah, so the recovery of heat sensitive material, because sometimes in essential oil, if we use in the room temperature, the temperature is too high, so we have to make a vacuum distillation, and then vacuum distillation is quite expensive, so we can use extraction. Okay, I think 2 years ago, at the end of 2019, I went to not a museum, yeah, museum at Siri, yeah, if you know it is in Solo, something over there, in East Central Java, and they extract many herbs, or like rosemary, or uh, flowers and so on, and then they show me the unit operation, and some of them are using distillation or steam distillation, and some of them are using extraction. Okay, now back to here. So let's have a look, and then I think it would be good if you can practice with your own. Maybe you can use your tablet, or you're using your books or something, yeah. Okay, this is we call it equilateral triangle, segitiga sama sisi, and then we're gonna use this for the graphics, to calculate, to understand the equilibrium, and also later on the operating line of the extraction operation. Okay, usually we have, so because we have, okay, how to use this one, yeah, how to use this one. I would show you that, let's say, let's see what is the name in here. Okay, for example, this is PQR, yeah. Let's write this as P, this is Q, this is R. Okay, rule number 1. In this triangle diagram, when it is in the sudut, yeah, in the sides here, or the topic, the point here, in this point, the composition would be only one, which is the particular compound. So here you will say this is 100% P, this is, we'll call it 100% Q, and this one is 100% R. Okay, got it? Okay, now how to find, let's say, how to find, for example, 50% P and 50% R. Okay, if it is only have two compounds, you may want to see uh, the two compounds between P and R. Okay, so this is P, this is R, so 50% P and R is between these two type. Okay, and then and then you can use your ruler and then find the ratio, which is 50% to the P, 15% to the R. Okay, so this one called then it's gonna be looks like a binary one, yeah, the one that you learn in bahan konstruksi, yeah, how to read this one. So this is actually become 50% P, which is corresponds to 50% R, or sometimes we call it 50% R. Okay, so and then for example, how about 25% R and 75% P? Would you go to upwards or downwards? If I want to find 5% of R, that one or that one? It looks like lever rule or the inverse rule. So you want to go here, yeah? Why? Because if this is 100% R, this points means 0% R, and now you can use your ruler to find the scale from 0% R into 100% R. Okay, got it? Maybe this one, if I divide it into 2, maybe about 20% R. Okay. Okay, so it looks like a scale, yeah? Any question up to here? Or is it clear enough?
So far it's still clear, I think.
Okay. Yeah, right. Okay, that's also the same, yeah, between, so if it's only two compounds, you just consider these lines. Looks very similar with the inverse rule in bahan konstruksi, yeah, because it is also about phase diagram. Now, how if it includes three compounds, yeah? How if it include three compounds? If it includes three compounds, then you want to write in this point, let's say, yeah? Okay, these points. Okay, now I would write this is P, this is Q, and this is R, which is similar with the previous one. Now, in this point X, for example, yeah, the question is, this is how many percentage of P, how many percentage of Q, and how many percentage of R. Okay, one point that percentage of P and percentage of Q and the percentage of R, the sum of them is 100%. So once you know the percentage P and the percentage Q, you can find your R by just subtracting 100% with percentage P and percentage of Q. Okay, now how to write this one? The percentage P, you want to revert into this P, yeah, there. So what you need to do is you make the line, or which is perpendicular, tegak lurus, with the base line that is perpendicular to the P. Okay, so this is the P, 100% P. So this line tells you about 0% P. Okay, and then from this point, which is this is a point that we're looking at, of draw the line to here and then measure them. Okay, and divide it with the T. This is the line which is perpendicular, tegak lurus, from the P to the base. Okay, so I will write here percentage P and then use your ruler. So I'm gonna use my line here just to check the sorry, the okay, It's a line. Okay. From here to here, I read it. Okay, it's bad. Um, yeah, from here, it is maybe about 2.1 centimeters. Okay, just keep in mind 2.1 centimeters. And after that, I also add uh, also uh, calculate the line from P to this one, which is 11.02. Okay, so my percentage of P now is from my calculation is 2.1 divided by 11.02. Maybe you want to help me with check with the calculator. So it is 2.1 divided by 11.
0.19.
Okay. Yeah, thank you. So this is 0.19. Okay, so the percentage of P is around 19%, comma, let's say 0.6. Yeah. Okay, yeah. So this tells you that P is this one. Now, to find, you may want to check, for example, you want to find the percentage of Q. So you can use the Q as the point here, and then find the line that is perpendicular to the base, yeah, tegak lurus, and then you also calculate the that one, yeah, just to measure the line. So it is 4.28. No. Yeah, 4.15. And then I add more. And the base is the same, yeah, but the base should be the same because it is yeah, oh, okay, just a little bit different. Okay, just write it, yeah, 12.7. So percent Q is 2 point, I forgot. uh, just okay, so this one is 2.46. 2.46 divided by 12. Usually this should be ini ya, per segitiga sama sisi ya, should be, but in this case it's not really triangle there. Okay, so how much, Dama, do you want to try?
Yes, already pakai kalkulator. It's 0.2036.
So
20.36.
okay, so yeah, so 20.36, yeah. Okay, so now yeah, so this tells you that this is contain about 19% P, and then about 20% of Q, and then your R you can just subtract them from 100%, so it becomes, can you help me to find this one? So 100 minus this one and minus this one, about 60%, yeah. Okay, yeah, and then and then you
It's
just
60.58.
okay, right? Okay, so yeah, so that is the uh, okay, so that is how to calculate the points, yeah, to find the composition in each point inside this triangle diagram. Okay, uh, for example 19%, 20, and then the other you just subtract them with 100. Yeah. Okay, any question up to here? Okay, so let's have a look the next one. Okay, yeah, this tell you the real one. For example, this point, yeah, if this is so then uh, here your the I think this not mm, yeah, it's not the ABC. It should be this should be the R. Yeah, this one, so here you can see that your R is actually 58 divided by 100, so it's 58%. This one B is not B but P, yeah, in this case, which is 20 divided by 100, and the last one is the 22 base here 22 divided 100, which is 22%. Yeah, so that's how you read them. Yeah, how you read them. Okay, uh, just I think my explanation is also quite clear. Okay, so to make easier, sometimes of course we use the scale. Let me check if they still use PQR. Okay, they still use PQR. Okay, so this is all the scales. If you want to find the uh, if you want to read the scale, so you don't need to just use all of your ruler. Yeah, let's say let's see the R here. Okay, uh, this is tells you about 100% R. Okay, and this tells you about the 0% R, because this is the base that is perpendicular uh, to uh, the points there. Okay, so for the R here we're gonna see the red scale. Okay, so red, yeah. So here this is equal to, this line tells you 0% R, this line tells you 10% R, 20%, 30%, 40, 50, 60, 80, 0, 10, 20, 30, 40, 50% of R, 60, 70, 80, 90, and then 100% R. Okay. Now for the P, what color of the lines you should use to find the scale of the P? Is it the blue one or the green one?
Green one.
Yeah, the green one, Nadifa, right. So because you want to find the line that is perpendicular to your points there. Okay, so if you want to find um, your scale for your P, you start from 0% P over here, yeah, 10% P, 20%, 30%, and so on up to 100%. Okay, so it leaves into the percentage of Q. If you want to find the percentage of Q, you follow the blue one. Okay, now I have a little bit of exercise, so have a look, and then I'm gonna be asking you which one. Yeah, so which one? So I'll make maybe about 5 minutes to write what is this point, the composition. Try to read this one. M, N, L, and K. Okay, while I grab some coffee or something. Okay, so have a look, 5 to 10 minutes, try to familiarize with this formula, and then read it, the composition in each one. You should be able to read it without the using the ruler, because there you have the scales. Yeah. Okay, so let's maybe try it first from, who wanna try? Ilham, do you wanna try the point n, the composition for point n? Come on. Ilham, are you there? Ilham? Oh, oh, okay. So, okay, your mic doesn't work. So, uh, can you write how many percent for the percentage of the P? P in N. Each scale is 10%. So, what is the percentage of P in the point N? If you want to check the P, you want to look at the green one here, yeah, from the base there. This is 0% P, and then this one is, can you write it? 0% P, and this is, come on, 10%, yeah, 10% P, this line, this is 20% P, 30%, 50%, yeah. So this one, the point here is actually 10%, yeah. Or if you want to draw with your ruler, you can get that. For example, find the ruler from 10% divide by this one. It's also so one scale divided by a 10 scale, that again become 10%. Okay, how about the R or the Q? Okay, now Alisa, what is the percentage for the Q in the point N?
I think it's around 70%. Is it right?
Yeah, 70%. Yeah. So you want to read this one, the red one. Yeah. So this is 0%. This one is this line is 10%, 20, 30, 40, 50, 60, 70. Yeah. So this tells you about 70%. Yeah, that's right. And how about the R, Alisa?
For the R, I think it's around wait,
Just
20%.
yeah, 20% based on 100% minus 80, so it is 20%. Okay, if you don't believe that it is 20%, you can try to check with the R. Look at the blue one. So the base of maybe from here, I'm gonna write it. So this 0%, this is 10%, that's 20%, and then look at it is in the same line, so it is 20% of what. Okay. Right, next. How about the M? Gamma. Gamma.
Yes.
Yeah. Have you tried it?
Yeah. For Q, it is 40.
Q is 40. Let's have a look. For M, yeah. Q.
Yeah.
Nope. Q is over here. So you started from the
Oh
red
no,
one.
it's miscounted.
0, 1,
30. It's
2,
30.
3. Yeah. Okay. And then the
Oh
percentage
wait, that
are
means I have to recount it. Hold on. So that means for P it's 98. 50 for P.
which one? For the P.
Yes.
Okay. So the green one, yeah. For the P, that would you code it from here. So this is 0, 1, 2, 3, 4, 5. Yes. So it will leave out your R. That would be
20.
yeah. Okay. Okay. Thank you, Kama. So yeah, that's sometimes a little bit confusing, but yeah, it is a good of course a very good start. Okay, Hadian, are you there? Hadian, can you help me to write the K?
Yes, miss.
Yeah, okay. Hadian, please try it. Which one do you want to find first? Percentage of P, R, or Q?
P.
P, okay. So for the K, how many percent of the P? So you would like to see it from the green one. So 1, so 10%, and then so uh, this K is how many percent of P? So this is 0%, yeah, 10%, 20, and then 30. Yeah, do you got it?
Yes, miss.
Okay. Okay, good. How about the Q one? For the Q, yeah, please, yeah, using my step before, you want to see from this is the Q, so the one that perpendicular is the line there, which is the red one. Okay, so for the this point K, you're gonna start from here. So how many percent of the K?
So 20, miss.
Yeah, good, good, good. And how about the remaining, the R?
50.
Yeah, 100% minus this one.
50, 50,
Yeah,
miss.
good.
50.
Okay, excellent. Right. Okay. This one is about. Okay, I think this one is similar. Yeah, just maybe a little bit of how. So with this one, you in any points you should be able to find first. Just find the point itself. Okay. The find the points is very important exercise because later on we want to find the the composition. Yeah, the composition. Usually a typical question would be, okay, how to do the uh, for example, what is the composition of the extract, what is the composition of the raffinate. So you should be able to read it from the graph. Okay, there's no quiz for today, but next week, next Thursday, I will give a quiz for you. Yeah. Okay. So just keep in mind, just try to follow them, and then if you don't understand, just yeah, just let me know. Okay. I think your friends also wait for that. If I need to repeat the questions. Okay. Now, let's say in any points you should be able to read. Okay, now I would say I have a point, a composition of M. Yeah, this point that M is tells you point, and M, let's say this M, let's have a quick look that it will have this M will have how many percent? 1, 2, 3, 4, 5, 6. So the M contain 60% of P, and the Q is around 30%, and the R is the remaining is 10%. Okay, and I have another solution. That the solution have composition of N. So it's about 1, 2, 3, 4, 5. So 50% of P, and then R is 30% of. Sorry, 20% of. Sorry, N is. No. N is 20% of P. Yeah, I misread. 20% of. Just read it. 20% of P. The Q is around 50%, and then the R is the remaining, which is should be about 30% of R. Okay, now when I mix them, so and then I mix them between the M and the N. Okay, the resulted mixture will depend on how many M and how many N. Yeah, let's say I just mix them 1 liter of M and 1 liter of N, so the ratio is 1:1. And if I put them using the mass balance, you can find the mixture now become 2 liters, and then you can calculate the composition. Okay, to calculate the composition, you can find it from this one, from this phase diagram. Okay, this line tell you the ranging composition of the mixture. Okay, and then this points telling you the composition of the mixture, and this line, yeah, the line from M to the points mixture and from point mixture to the N tells you the relative amount of the each solution. Okay, we're gonna use lever rule again. So if let's say this is M and O, yeah, let's say O. Okay, so the amount of solution M is actually 1, 2, so M is here, so using lever rule is actually this one, yeah, remember lever rule? So it's actually one part. I would say this is only one part. Okay, the amount of solution N, because N in here, and then this is the line between M and the points O, the mixture, it is 1, 2, 3 parts. Okay, yeah, so that's so this tells you that they mix the 3 parts of N with this composition and 1 part of M with this composition. For example, they mix, for example, 3 kilogram of N with 1 kilogram of M, and this is gonna be the mixture. Okay, the mixture will have 4 kilograms, and this is the resulted composition. Okay, yeah. So if, for example, how about if we mix it at 1:1, yeah, for example, 1 part of M, like for example 1 kilogram of M and 1 kilogram of N. So then you have to find with the line here, which is the ratio should be 1:1, so maybe it would be moved in here. Okay, got it? Okay, so here, yeah, the ratio, the amount of M and the ratio of N, again, you have to use lever rule, the one that is our inverse rule, where if you see this point N, then this is the amount of N, which is about 3 parts, and if this is the point M, this one is the 1 part. Okay, and again, it's actually we use a lot, sometimes in mole percent or sometimes in weight percent, but usually I think we use a lot in weight fraction. Just give me a sec. Yeah, for extraction, it can be yeah, it depends. It can be in mole percent or it can be weight percent, but of course if you use different unit, then maybe the equilibrium would be different as well. Yeah, the type of the graph later on. Okay, so okay, so this is the last one for this slide, but we have 7 part up to for next week, so gonna be a long time. Okay, so now try to imagine we have the feed, yeah. The feed is actually for this case about 30% of P, and then 30% of Q, and also 40% of R. Yeah, this one. if we calculate the equilibrium, let's say there's an equilibrium, and after we mix them, for example, in the feed, after it goes to equilibrium, it will be separated into extract, EK, and also RF, or raffinate. So, for example, this is the raffinate. Maybe, for example, this is from the equilibrium composition. So you should be able to read how much the extract do you have, and also what is the remaining raffinate do you have. Okay, can you read it here? So what is the extract here? So the extract will contain, this is P here. P is 10%. Okay, and then the Q is become 40%, yeah, and R is the remaining, so 100 minus 10 minus 40, so it would be 50%. Okay, so this one there. Okay, and the raffinate, you can also write it here. So the raffinate, if I read it from here, so it should have P, so the P would be about 90% P. And then how about the Q? Because it is in the baseline of the Q, so there's no Q. And then the R is only 10%. Yeah. Okay, so this tells you the raffinate. So it tells you that it moves the feed, yeah, from the feed. Here it becomes the extract. So most of the Q is going into the extract phase, yeah, to the 40% there, while the if you look at here in the raffinate, there is no Q. So that's the idea, how to change or to move those Q content, or usually the Q is this, maybe for example from here to that one. Okay, yeah, so that is the end of the extraction part. Part 1, it is just not a dummy, just a very a very yeah, just the beginning for the concept. Okay, now let's have a look on the next part. Okay, here. So yeah, previously we have an example on A, B, and C. Just give me a minute. Yeah, just give me, okay, just continue. Okay, now so this is a typical phase diagram, a typical phase diagram for extraction. Okay, so what is the information that we can draw from here? So in each point, the 1 point composition, it actually reverts to an equilibrium. It goes to the extract and also the raffinate. Yeah, so every for example, if we have composition in the two-phase area, in equilibrium, it will separate into the extract and also the raffinate. Okay, the convention here, we use C as the solute. Okay, the one that we want to be removed from the original solvent is solute. Yeah, we want to, for example, we want to remove acetic acid from water. So the acetic acid is the solute, and then we put it on the top in the C. Okay, A is the original solvent. Yeah, so this is the initial one. Okay, so we want them to be a lot of them in the raffinate, so this is close to the raffinate, and the extract is this one. It is based on the B, which is the solvent extractor. Okay, of course you want to have a very high extract, so the high extract should be around this area if possible. But if your equilibrium curve doesn't permit that, so maybe this is the maximum around the maximum. Yeah, and this one tells you the plate point, which is there is no separation between E and R, and this one is just outside the range for equilibrium. Okay, and each point around this area, it will be differentiated into separated into extract and also the raffinate. Okay, so what is the equilibrium data looks like? Okay, so it is looks like this. So at a certain pressure and temperature, this line tell you the composition of the extract phase, which is equilibrium with the composition in the raffinate phase. And if you're given with these tables, you should be able to construct the phase diagram for the liquid extraction. Yeah, because from A, B, C, you can find one point in this triangle diagram, and the raffinate as well, you can put it in the diagram, and then you can just make a line from the extract to raffinate, and that is your tie line. Okay, usually again, because we use a lot in the practice, we use a weight fraction. Yeah, we're not using mole fraction, but we use a weight fraction. Okay, when we increase the temperature, if we increase the temperature from T1 to T3, the area of the equilibrium become smaller and smaller, and then we know that we want to find around this area, yeah, with the extract with the solvent. So we use the extraction in lower as a lower temperature as possible, and also in order to reduce the solvent, so the solvent doesn't evaporize as well. Yeah, so similar to absorption, in the extraction we use it with the lower temperature. Okay, now let's have a look. This is maybe a topic of the quiz for next week. We want to find the mass balance. Yeah, the mass balance of an extraction of one batch. Okay. Okay, it's almost 11 o'clock, but that's fine. So let's say we have a feed which is 100 kilogram, and the composition is a 7% of A percent weight, and there is no B, of course, because there's no solvent at the time, and a C. So the C is the solute. Yeah, or the, yeah. So here I'm just gonna write it. This is the solute. This is the original solvent. Okay, and let's contact them with the solvent, and the solvent means only containing B. Yeah, there is no C, there is no A, it's just the other typical extractor. For example, I have tea in water, I just contact it with organic solvent. Yeah, so this is 100%, and the solvent is 50 kilogram. Okay, with this essence you can find the ratio between your feed and also your solvent. It's gonna be important later on when you find the mixture later. Okay, got it up to here? Yeah. Then we mix them together with the agitator, with the with the good mixing, and once it goes into the two-phase diagram, the two-phase here, then it's gonna separate it into an extract and also raffinate. Now the question is, what is the composition of the extract, and also how much is the extract that we have, and how much is the extract, how much is the raffinate that we have, and also how much is the composition that we have. Okay, so first we need to find the equilibrium curve in the triangle diagram in this condition. Okay. Okay, so what we do first is just to rewrite. So the feed is 70% A and 30% C, and there is no B. Okay, because it's only consists of two. It only consists. It only consists of two components. Yeah. Then we use the A and C. Got it, anyone? Yeah, to find the composition. Okay. Yeah. Now, and then find where is the 30% C. So this is 100% C. So with your ruler, you find which one is the 30% of C. Okay. So this is 0% C. So and then you find your ruler and then divide it by to find the 3/10, yeah, of the this one, and then you got this is the feed. So this C, and then the remaining is A. Okay, so your feed, you can put your maybe with the color, maybe this one. Okay, this is your feed. The next one is you have the solvent. The solvent is 100% B. Okay, so find where is 100% B. This one. Okay, got it? This is 100% B because there is no C, there's no A, only 100% B. So this is 0% B. Okay, and then the next one is draw your line from F to S. Okay, find your line from F to S there. Okay, now the next so and then here now you know that F is 100 kilogram, S is 50 kilogram, so the total mixture is 150 kilogram. Okay, to get the point where is M, what you need to do is to use the ratio. So F to S ratio is 100 divided by 50. So it is 2/1. So you will have to find somewhere along the triangle diagram with your ruler. Find it where is 2 near the S because it's lever rule, and 1 near the F. So here is the line. So maybe you want to check the line, the temperature or the length. Yeah, 12.71. Okay, so then find one part for the F and then 2 part for the S. So maybe around 4 something. Yeah. And then this one, yeah, maybe around 4 something. So this is where you put the points there. Okay, so that's why they put the M there. This tells you that this is this is 2 part and this is 1 part. Yeah, 2 part for the feed and 1 part of the S. Up to here, any question? And then you got the M points. Is it clear enough, or you need more explanation about the how to find the M, the mixture? Come on, anyone? Is it clear enough, or still a bit confused? Nadifa, what do you think?
For me, it's clear, Bu.
Okay, Helena, how about you?
Still digesting, ma'am, but I will review after this.
Okay, okay, don't forget just to pause and then replay again, yeah, after I put it here. Okay, so if for example, I don't want 50 kilogram, I want to have 100% 100 kilogram of solvent, yeah. If you have different, for example, yeah, you want to have 100 F and also solvent 100 as well, then you have to divide this is equal to 1 by 1, because this is the ratio of feed is 1 and also the solvent is 1, so maybe around this one. Okay, so the ratio between the feed and the solvent will determine which one is the solvent, yeah. Let me know which one is the mixture. Okay, just let's say we have the mixture there. Now the next my next question, yeah, it would be always on the quiz, is how much how much the extract that I get, how many kilograms of extract that I get, and how many raffinate from the after the mixture that I get. Okay, that's important because we want to multiply to get the value of the product. We have to multiply the composition and the amount. Just give me again 1 minute. Okay, yeah. Now, so for example, from this 150 kilogram, which one goes to the, because after we mix them, it's gonna be separated again, right? So which one goes to the extract, which one goes to the raffinate? Yeah, so that is the next question. The next question now, to get which one goes to the extract and goes to the raffinate, again, we have to check with the ratio again referral, yeah. Extract is around this one, yeah, so the extract divided by the raffinate equal to, okay, the length of, this is the extract, so with referral you want to find the one that just inversely, yeah, around this one, so the rm, the length of rm, and divided by the length of ME. Yeah, this is the raffinate, so this is the length of ME. So using your ruler, you divide them. You use that with your ruler. For example, this one is, yeah, this one, for example, how much from here? 5 point, so ME is 5.16, and this one or 9 something, yeah. So or maybe one more. So here the length of RM that I divide them is around 466. Okay, and then the one that is for this one is, for example, here is 5, so 4.6 divided by 5, so yeah, around that one. So and then in the here maybe this is still approximate, yeah, still approximate. Then let's say you got it, for example, the ratio of RM to ME, let's say 5/6, yeah, from this one there. Okay, so your extract becomes 5 divide by the total of this one, 11, multiply with the mixture. The mixture is 150 kilogram. Then you will get the amount of extract, and also you will get the amount of raffinate. Yeah, so then you calculate that one, the amount of extract, and also the amount of raffinate. Okay, and then so that is the amount of the extract and the raffinate that you have. The next one is how to read the percentage. Yeah, you can say, so the percentage of A, again you can see this one, yeah, with your the triangle diagram, remember, and then with the triangle diagram you can find which one is the percentage of A and the percentage of R. Okay, so that is the typical one. Okay, and up to here, any question? So this is the typical question in the quiz, or you can see other problem solving that you have in the Himatek, for example, or yeah, it's all quite similar. Okay, but I don't want to give the assignment about this one for you now, because the triangle diagram, the segitiga sama sisi, yeah, we don't use very much, because first it is difficult to read. Yeah, you have to miring, yeah, to read them. And the one that is in particular that we want to see, usually the C, the solvent, and also B, the solute, and also B, the solvent. We don't really see the A, because we can get the composition of A by finding the composition C and B. Okay, because of that, if you look at the next slide here, rather than using the segitiga sama sisi, yeah, this one, the triangle, then we swift them into a right angle triangle, segitiga sama siku, ya, segitiga sama kaki, segitiga siku sama kaki. Okay, why? Because here we can read up to here we can read the percentage of B, and then the vertical one we can read the percentage of C. Okay, so rather than we use equilateral triangle, we swift them into a right angle triangle, but of course the equilibrium also will be shifting like this. Yeah, it's like you have I don't know what is that, maybe a balloon or something, and then you try to swift them. Yeah, so everything's of course going to be swifted. Okay, so it is easy to read, and it is easier to read, of course, and then you just need to read the percentage of B and also the percentage of C, and then you can find the percentage of A by subtracting 100% minus percentage B and C. Okay, so the next part we're gonna use the right angle triangle. Yeah, okay. All right, so let's see, can I maybe, let's try to pull it like that, because I won't read it, maybe I won't write it too much. Yeah, just make it easier. Okay, so in a batch process we call it the stage 1, and then this is stage 2, and it is called cross current process. Yeah, a cross current extraction, 2 stage, stage 1 and stage 2. Yeah, let's see this case where we feed its contact with the solvent, 100% B, and then we got the extract. Okay, but we still have some more left in the raffinate. So what we do is to the the raffinate itself is extracted with another solvent. It looks like you have a tea bag, yeah. You put it in the first cup of tea, and then sayang, yeah, you still have some more tea left in your raffinate in your remaining tea bag, and then you put it again to the hot water. Okay, so then you got the extract. Maybe the extract number 2 is not as rich as extract number 1, but it is still much better because you still can get it out the tea from the tea bag. Okay, the you can still get the flavor even it is not as dense as the previous tea. Okay, so this is called the cross current extraction. Now, how to draw the cross current extraction? So let's have a look. So here, okay, so first again, we have the feed. So the feed always have, I think it's still better if I write something, yeah? Is it okay? Okay, so still better if, okay, so the feed always lies on this vertical one. Why? Because mostly the feed doesn't contain B, it only contains percentage of C and percentage of A. Okay, I have no problem writing in here. Okay, right. Okay, so let's say this is the feed, and again the B, usually the B is 100%, but in some cases the B still contain a little bit of C, so maybe around this area. Okay, the B. Okay, so the next one, how to so the first stage, I'll write the steps so you can maybe check it again. Locate F and S in the triangle diagram. Okay, the next one, okay, draw line F and S. Yeah, draw the line there. Okay, and then so again I'll write it again, find the F and the S, and then draw the line, and then find the M. How to find the M, the M1, using a ratio between F over S. Okay, you should know how much is your F, the amount of F and the amount of S, and after that you can find the mixture. For example, this is the ratio between F and also S, and then this is your M. Okay, and after that, once you got the M, look for the tie line that pass via the M1. Okay, and then you will got the E1 as the extract number 1, and the extract and R1 as the extract number 2, so as the raffinate. Okay, so this tell you again with this one. So this is the feed, this is located in this one. When I explain the graph, I always reverse to the schematic. Okay, it might be beneficial for you as well. So when you do the assignments or do the exam, look and understand the concept rather than just look at the graph. Okay, if you just look at the graph, it's gonna be difficult. Okay, and then the next one is we have the S, yeah, there, and then you have the mixture here, M1, and then it will reverse to the E1, which is you take it out, and the R1. Now the R1 will act as the second feed, this feed for the second stage. Okay, so R1 now will act as the second feed now for the stage 2. Okay, and then you add the S again, and after that with the S, yeah, this is the S like that, and this one is M. You have the mixture number 2, and then with the with this tie line you end up with E extract number 2 and also the R number 2. So if I go back to here, so in the second stage you will have the mixture M, and then it will leave you out with the extract from stream number stage 2 and also the raffinate. If you want to enrich all of them, you got the extract, you can get it more. Yeah, you can maybe just extract the raffinate too again, just extract. But then if you look at here, it's gonna be very thin over here. Yeah. So here we can find the number of composition of R1, R2, E1, E2. It also can be as explained. Okay, so with right angle diagram, it's easy to follow, and then but when we do the third stages, it become very difficult around here, yeah, because then the R2 become the next feed for the stage 3. Then you, yeah, when you draw the line, it would be become a little bit of difficult. So next week we're gonna talk about the using of XY diagram again, another diagram, just to solve this triangle diagram. All right, I think that's all for today. So I think in this 1 week you can process the before there is no assignment, there is no assignment for me for about this extraction. I think it is much better if you can do the pack columns right away, because starting next week I will give a lot of quiz to you about extraction. Okay, usually there are 6 quizzes, but I'm not sure, so maybe half of them as a assignment of practice in the class, or half of them is become the quiz. Okay, I think that's all for today for me. It is almost 11 as well. Any questions?
Oh, can you post the recording?
Oh yeah, now yeah, should be okay. Right, thank
Okay,
you.
thank you, ma'am.
Okay, all right. Thank you everyone, and then I'm gonna see you again next week, and then yeah, I need to post to Dama as well, yeah, about the schedule for the tricolumn. Okay, thank you everyone. Bye bye, and have a good weekend.